Dear speakers, first, thanks a lot for joining us today for this IROS 2020 workshop on managing deformation. So this session will be recorded and will be freely available to download. And so for this session, I would like to make a brief introduction. So the ability to interact with deformable objects of any scale is a prerequisite for advanced robot autonomy, ranging from grasping and handling everyday objects such as food, clothing, etc. In consumer robotics and in surgical procedure, you will see robots that manipulating tissues and guiding flexible needles. In agriculture, you see robots picking up fruits, even make food in the kitchen. And in industrial settings, flexible objects such as cables and ropes are also some other subject that could be manipulated by the robots. However, taking into account deformation introduced new challenges, in particular, the complication of sensing deformation, the curse of infinite dimensionality of the deformation configuration, and the complexity of high linearities in modeling the deformation. Therefore, new paradigms need to address these challenges. The aim of this workshop is to discuss new research prospects, considering the object deformation in various robotic applications. So today's session, the name is Produce, Assemble, and Build with Deformable Objects.
And today I will briefly explain about my research on robotic motion control and planning and deformation. And I mainly research on the robotic manipulation and its application to the industrial automation. And today I would like to explain about the three topics on flexibility in robotic manipulation. And one is the motion planning, and the second one is the feedback control, and the third one is the error recovery. And the first, I would like to explain about the two topics of motion planning and feedback control. And this is a typical case of the flexible object manipulation used in an assembly. And this is the human assembly of oil seal. And oil seal is made by rubber, and it has a ring shape. And to assemble it to the outer surface of the cylinder, or outer surface of the piston, or inner surface of the cylinder, the human is very, very skillful enough that can assemble these flexible parts very fast and very skillfully. And we consider replacing this task by using robots. And first, we constructed the dual assembly planner to assemble a ring-shaped object to a cylinder. And in this case, what we have considered is that we use the index function to plan the motion of the dual manipulator. And the index function is composed of the collision avoidance and minimizing the elastic energy. And that motion is constructed along with the help of the physics simulator of the assembly of ring-shaped object. Then I would like to focus on the feedback control. And in this case, first we use the human demonstration to extract the force control law. And in this case, the horizontal direction is y and the vertical direction is x. And we found from the force and positional response that in x direction, the motion is like a spring-like motion movement. And on the other hand, in the y direction, it is the damper-like movement. So we decided to apply the stiffness control in the x direction and the damping control in the y direction. Then we consider optimizing the force control parameter of the position of the damping control and stiffness control. And by optimizing the force control parameter, we could successfully reduce the peak force to 63%. And it is very close to the level of human assembly. Next, we would like to introduce the second topic about the error recovery in snap assembly. Actually, we focus on the assembly of plastic parts, including snap joints. And in this case, the parts with snap joints is very easily to be assembled, but it is very difficult to be disassembled. Hence, it is very important to identify the error state before the error actually occurs. And in this video, the top video shows the successful case. And on the other hand, the bottom video shows the failure case. And this slide shows our algorithm. And first, we in the training phase, we obtain the force torque profile during the assembly, and we consider extract the feature. And then we consider train the feature by using SVM and classify the error states. And in the execution phase, we first consider identify the error state, and then the error is identified before the error actually occurs. And then after identifying the error, we consider recovering from the error state. And this is the successful case of assembly. And this is very normal. And first, we consider stop assembling the object before the actual the assembly is completed. And then this shows the error state. And in this case, the error is identified. And then the mail part is lifted up again, and error is recovered, and the robot is tried to assemble the mail part again. And this is the final case. In this case, the error is identified. The robot tries to identify the error, but the accuracy of the identification is not large enough. So the robot additionally moves the mail part in the horizontal direction to a little bit, and then try to identify the error state again. Then robot recognize that the robot going to make error. Then robot lifted up the mail part and modify the position of the mail part and try to assemble it again. Okay, thank you very much. This is the end of my talk.
My screen, give a little overview. So yeah, thank you for inviting me. I'm Mathew Schwartz. I did my undergraduate in University of Michigan in design and sculpture. So that kind of starts off with addressing one of those questions. And after that, I went to Michigan for my Master's of Science in Architecture. And after then, I moved to Seoul National University, and I was a full-time research scientist at the Advanced Institutes of Convergence Technology with Jihong Park, who manages the Dynamic Robotics Systems Lab. And through there, I connected my interest in human factors and research with robotics and manufacturing, because his lab focused on torque control, full body robot control of humanoids. Since then, I had a short time in Nanyang Technological University in the Rehabilitation Research Institute, and now I'm an assistant professor in architecture and design at NGIT. So in general, my interests are in automation and design, and that kind of breaks into automated creation and automated evaluation. On the creation side, it's between creating 3D models for design or fabricating, actually making the design. And in evaluating, I look at human factors. So this could be done through manual evaluation. And the human factors link back into the 3D model, which is also connected to the fabrication of that model. This was Gwangyo Techno Valley in Suwon, South Korea. This was the view outside my office, and the buildings here were not there when I moved in, and 3 years later, it looked like this. And this kind of inspires a lot of my interest in how important it is that we bring construction to an automated state. During this time, one of the cranes fell from the construction site and killed someone. And it reinforced the need of how we can do such complex robotic manipulation. We have the DARPA Robotics Challenge, and yet we still have people inside of these tiny boxes, hundreds of meters in the air, doing this manual work. And it's also repetitive. So each floor is identical, which is such a good topic for robotics. Back in 2012, one of the works I was inspired to do with Jason Prasad was in sculpting clay. And the sculpting clay was for minimal waste molds. And one of the inspirations here was because of my undergraduate in sculpture, we commonly use oil clay to make sculptures, then create a mold off of those sculptures, and we can reuse that clay. So here's some videos of this process where the robot would sculpt the clay, and through it being oil clay and not water clay, we custom made the mixture ourselves, so from the soil itself. And that allowed us to, being young and not as good at robots, also mess up, right? And because it was clay, you could make a cut or a nick in the clay, and then you would just push some clay back on and recut the same path. And you didn't have to worry about the costs of ruining in a really expensive mold. So on the top right video, that just shows we did the top and bottom of the chair, which is shown in the top left. Both of those had two different molds, but they used the same clay. So we just compacted the clay and recut the clay for a new mold. And in the end, it was laid up with fiberglass. So ideally in the future, I wouldn't want to use a manual fiberglass layup, but instead we use another robot to spray the fiberglass. In the end, the chair would hold me, quite heavy, and it was quite thin. And another project that I think is relevant here is in the difficulties of these simple tasks like floor tiling. And this brings back the motivation from a human-centric perspective. Why do we have people that are in a bent over position on the floor, hand laying all these tiles? And what I would really like to have done is something that is so simple, but ends up being complex for a person, at repetition can create something like a mosaic. And this was just an initial experimental approach where we use motion capture for localization of a small humanoid robot that we thought we could place this into someone's house and it could help them tile. So we looked at, could it pick up the tile? And one of the challenges here was in the gripper. So we needed to create some sort of gripping mechanism that would allow this robot that didn't have hands to be able to pick up a flat tile. So now, in this case, the manufacturing material itself was rigid, but the gripper had to be soft and deformable in order to interact with it. So where do I think this can go? This was a general concept that I wrote about in a paper a couple of years ago. It was this idea between a split between architecture and engineering in the top left and bottom right axis. And currently, in my opinion, a lot of the work that we're doing in architecture and design is using a robot like a CNC machine. It's saying we have an industrial arm, which has been around for 40 years, 50 years, and we use it pretty much the same. And that means inverse kinematics position control. And I think in engineering, a lot has been going on towards torque control and understanding dynamics that happen in real time and responsiveness to those materials. So I think the future here really is about, especially from the design perspective, how we can create some new algorithms that leverage torque control that would make something possible that hasn't been possible in the past. Meaning, because of the algorithms synthesized with the method of control, we're able to create things that we really couldn't have created in the past. And not just, it's an easier way to do it, but actually better for the future. So that's it from me.
Of you mentioned the fact that maybe to handle deformable objects, we need torque control. Do you think so how could we model this this torque feedback? And do we really need to sense this the object deformation, or will we be able to manipulate deformable object without torque control? What do you think about this? Or do you think everything is solved in this direction? Or maybe you think it's not a question, I'm not sure. I'm not sure who wants to answer.
Okay, and as I explained in my presentation, that to control the flexible object, I think that the torque control or force control is essential. Yeah, otherwise, the robot has to be very carefully controlled, not to make the elastic deformation to be small. But yes, my answer is that basically torque control and force control is necessary, and to measure the force, the joint torque or 6DOF force torque sensor will be necessary. Otherwise, we have to control the robot very carefully.
Okay.
Yeah.
I think it's required in all feasible aspects. So I can imagine maybe if you're in a vacuum of space and you know everything about the environment and all possible disturbances that could happen, you could use position control because you can guess where something would happen and where, how it would deform. But I think the value of the torque control is that you get a better sense of what's happening indirectly that wasn't accounted for in a computer model or simulation, like something like fabric, picking up the fabric, it folds in different ways, and being able to exactly predict how it would, I think is not immediately feasible for a lot of things. So in the case of torque control, a lot of focus has been on, I think, human-robot interaction, because you want compliance with torque. But I think there's a good argument to be made for materials that you don't understand exactly what is going to do or how it's constructed, like OBS board in architecture and the building industry is glued up of random particles. So you wouldn't be able to exactly model how it would act anyway. So there wouldn't be a possible, I don't know, maybe you do a CT scan and X-ray and try to come up with it, but I think it's not as feasible.
But when you deal with, Professor Harada, when you deal with this elastic shape, you have a way to model it. In a sense, this material, you can model its properties so that you know when it will break or when it will just change its shape. But
yeah,
maybe when we are going to some clay, this is not the same. Can we imagine something that will work for both, or do we have to imagine two ways of dealing with this control?
Actually, in my experiment, we first model the elastic object and then make the elastic deformation of the object as small as possible. But it depends on the model, and it depends on the accuracy of the model. So to obtain the accurate model of the elasticity is very important problem. And this is true, especially when the elasticity is very, very large. So in this case, we have to consider alternative strategy without strongly rely on the model. But this is not what I have been considered, and this will be the future of the story.
Okay. So if it's not possible to model the object. So you said this is maybe the future, and so how could we do with some clay or something? Maybe if we are considering clay, it's maybe a material that is also changing its model with time, because sometimes you will have more water inside. So maybe we won't be able to trust the model we built. And if you have some torque control or some force control, you will have to find a way to model the force control. So in which directions should we go, and how could we deal with that? Everybody can answer, even David or Andrea, if you have some ideas. You can still.
I cannot answer your question, Claire, because I'm also not working with force control. But I actually I don't know if I have a separate question from what you have asked, because what I see. So I have one question. Is that when I see Professor Harada's slide, I think you mentioned basically you ask human to perform the task beforehand, and you learn from the human performance. So this is what you mentioned in one of your slides, I think, when you try to assemble the ring object. So what I think is that it's because in machine there's a concept in reinforcement learning or imitation learning that is learning from demonstration. But I think what you have taken is a different approach, where you actually have an explicit model, and you just you try to fit the human data with this model to define the stiffness of the model. Is that what you did? So instead of having just a demonstration, you actually have and you learn from the data directly. You also have a model which you want to fit, so that you learn the stiffness where you try to. I think this is what is happening in one of the experiments. Am I wrong, or I just want to ask this?
Yes, in my experiment, you're right.
Yes. So in this case, so in this case, I mean, in general, for all of tasks, so do you think that actually human, when human try to perform this beforehand, it's always good that robot learns it from human, directly from the human manipulation data? Or you think we can also have a model-free approach, where we just simply, like, we don't try to fit it with a kind of model, because this is what you did. I think you have a model to model how human did the work, but you just simply learn from the data. Do you have, because now, I mean, deep learning is very hot topic also in robotics. What do you think of this in this kind of situation? Do you think we need the model, or we can just get rid of it?
And due to the recent advancement of the deep learning technology, I think that the situation is changing every year. And but what I have been thinking is that we have to focus on the feature of the elastic object, and it will be very, very difficult to learn everything from human demonstration, and it is also difficult to calculate everything from the model. So what I have been done is that by carefully observing the feature of the task, we have to determine, we determine what part of the parameter should be determined by human demonstration, and of which part of the parameter should be calculated. So, and this is a kind of task-specific knowledge, but and also this is very difficult to define which parameter should be demonstrated, obtained from demonstration, and which parameter should be calculated. Okay, is it the answer? Okay.
Yes. So this is an open problem now.
Yeah.
I think that basically what kind of parameter should we actually learn from? What is the actually feature that we actually need to learn from the demonstration? Okay. Yeah, I agree. This is a very complex problem. Yeah. One of the directions that.
Yeah.
Yeah, Claire?
Yes. So there is also something else that you said, Mathew, is that when you build a building, every stage is the same. So this is a repetitive task. And you said, so this is something that a robot can do because it's repetitive. And I was wondering with manipulating deformable object, are we still in some tasks that are really repetitive? Which part of the task is repetitive with a deformable object, and which part of the task won't be the same from one experiment to another?
That's a good point. I think more than just that a robot could do it because it's repetitive, it's a robot should do it because it's repetitive. So if every layer of a 100-story building is going to be done exactly the same way, and we want to have good tolerances, then we shouldn't really require people to do this type of repetitive manual labor without any input of creativity. So I think this is a good opportunity that robots should benefit society in that way. But yeah, there's a problem in the deformation of materials, and architecture and construction for a long time have focused on trying to standardize materials for these problems. If we just made traditional wood houses and we used the trees directly without any drying, without any pre-treating, it would make the building process much more difficult and expensive. So we spend a lot of energy and money and time into standardizing the material to stop it from being deformable. So I think there's a balance to this question, which is as the research for deformation improves, we can do things more on the robotic side with less upfront costs in treating the material for stopping it from being deformable.
Okay, thank you. And also maybe Professor Harada, so when you learn the parameters for one elastic that you want to put on this stick, how far could you change could you take another one? Did you take another one? Did you try to use what you learned from this one to do something else?
Yeah, and this is a very important point. At the time, which we researched on the topic, which I showed you in the first part of this workshop, I trained the parameter for specific object. But due to the recent advancement of the deep learning technology, the situation is changing. And recently, we are changing the attitude that first we train the basic part of the parameter, and then for specific task, we additionally train for the specific task and obtain the planner or controller for the specific task. But in this case, it is difficult to determine what is the nominal part and what is the task-specific part. But in any way, currently we are directing this direction.
Okay.
Yeah.
Just want to ask, try to ask one question regarding your answer, Professor Harada. So
yeah.
With this training process, how many data do you need? So for this, yeah, I was wondering.
In case of the reinforcement learning, it usually takes about 100 and 200 demonstration,
Mm.
and everything will be finished. And this is for the specific task. And first we train, for example, by using simulator for specific task, and then we can apply to the different task. And this can be done by using a real robot. So in this case, the number of training data can be much smaller than the case where we train all the we obtain all the training data from the experiment.
Oh, okay. But then in this case, I just want to ask one more question. Is there some gap between, I mean, if you just transfer your data from your simulation to robot, normally I think people say that there are some gaps if you want to transfer that. So how do you handle this?
I still did not evaluate the difference between the real data and the simulation. But at least what I can tell you that the simulation is very, very effective to reduce the number of training data which we collect from the real world demonstration, real world experiment.
Mm. Okay, so we have written some more personal questions.
Claire?
Oui. Yes.
Sorry. Yes, sorry. If I may also.
Yes, you can, of course.
A couple of questions. Yeah, it was, thanks a lot. Very nice debate already. So I was just wondering, you both replied quite convincingly and convinced about the use of torque control for this type of applications. So, well, the four of us are more working with vision. Personally, I didn't work with torque control. We use admittance control, which is a trick, as you may know, to avoid the dynamic modeling of a robot and make it compliant and so on. So I've always felt like torque control is a bit difficult to set up because you need some model of the dynamics, and well, of course, Jihong Park is an expert, and other people also in Europe, but I also wonder if other alternatives, like especially now, for example, and this was also something we discussed while we were setting up this workshop, is that nowadays there is a lot of buzz about soft actuators. So when you see them, it seems like magic. Then I don't know if it's so easy to use, and I wonder if with respect to what you replied before about the fact that you don't have a model and you want to, of course, not break the robot and not break the material. What do you think about using a soft actuator to manipulate a soft body, or admittance control? I don't know if you can give some more insight on it.
From my perspective, I think there's a lot of opportunity in the soft robotics and actuation. So I didn't show anything so far, but currently I'm working with Jan Lagerwell at University of Luxembourg in soft matter physics. And they've been developing liquid crystal elastomers to basically create a shell, and then you can actuate this shell at small scale, 1 millimeter scale. And we look at how could you aggregate these into some larger gripper that would have small kind of defects that you can create through heat or light, and that would create small actuations that would then mass and aggregate into some other effect. So at least from other work that I'm doing, I'm definitely thinking that there's opportunity there for that, and you end up creating the compliance through essentially the robot itself. If you consider the gripper part of the robot, then you offload some of the requirements of what I've been advocating in terms of the torque control for understanding that part into the material itself becomes deformable and compliant in that way. So I would say I agree on that.
So at the end, it can replace the torque control, or they would have different uses?
I think they have different uses. I took out one slide example. One of the examples I liked from how you could use torque control in architecture was this digging a hole for pipes. If you're digging a hole for pipes and you want basically no way to cause a problem through cutting into the pipe, if you physically limit the amount of torque that's possible to the motor, it would be able to cut through the soil and then couldn't cut through the pipe. So if you understand how much force is necessary to break a pipe and you physically limit it, then you don't necessarily need to rely on the algorithm behind reading a force sensor and then finding out at some frequency that you hit the pipe or not.
So it's kind of open loop. It's an open loop strategy where you limit the force.
Yeah, in a sense that we're trying to avoid problems. It's safety measures. So it's kind of my naive approach to what the advantage could be. Yeah.
Thanks a lot. David has a question, I think.
Can I? So question for the 5 of you. Okay, so since we are in the topic. No, like literally to the 5 of you. 1, 2, 3, yeah, 5. For what type of mechanical behavior should a manipulator have when interacting with very soft materials? Should it behave in a compliant way, or should it behave as a, as Andrea mentioned, as a very rigid, as a rigid structure? What is the best way that we should either control the robot or purchase a robot with such already intrinsic mechanical properties? Anyone? Very soft material. How should we control the robot to behave in a very compliant way, or should we purchase a robot, one of those that Andrea mentions with very compliant joints? What is the the best combination in your opinion and experience, or even with this elastic oil? How do you call those? O-rings? I don't know. Anyone? That's my provocative question of the night.
Okay, and at least from my experience, the manipulator should behave compliantly. So this is because the flexible object assembly, if the flexible object assembly needs to be precise, the manipulator has to be torque controlled, or force control will be necessary. But depending on the task, the gripper, in the gripper, whether we can use soft gripper or not depends on the task. For example, if we will have to grasp a very soft object, maybe we have to use a soft gripper. But the surface of the object is not so elastic, so we can use a hard gripper. So, but anyway, what I want to tell you, what I want to tell is that the manipulator needs to be torque controlled, but we can use the different gripper depending on the purpose of the task.
I was going to say similar thing, slightly different. So yeah, it depends. I think is too easy of an answer. I think it is really that the gripper itself should be deformable and change. So I think it's kind of like asking whether the shocks and struts on a car should be compliant or rigid. And it's like, well, you put some non-Newtonian fluid in there so that when it needs to be rigid, it is, and when it needs to be fluid and soft, it is. And I think that's how we should be approaching the design of the robots and the grippers, that if I need to drag something and need it to be compliant so it moves over some bumps or rocks, then it should. And at a certain point, it needs to be stiff and rigid and not compliant, then it should also handle that as well. So I think that's a combination of the material and the design of the end effector as well as the overall robot control.
why did you get interested in deformable objects? When did you come from rigid object to deformable object? And why did you get interested into this field?
In the manipulation of the flexible object simply because that I'm interested in the industrial manipulation, and there are a lot of elastic parts. So the elastic manipulation of flexible objects cannot be avoided, and also it supplies a very interesting research topic. So this is simply the reason why I'm interested in the manipulation of flexible objects. So I'm first interested in the industrial automation. Then I'm interested in the manipulation of flexible objects.
Okay.
One question. Sorry that I follow up to my previous question. It follows some vibrations coincidentally. So if the behavior we are trying to impose to the manipulator is compliant, therefore it has the capability to produce vibrations, and if it's interacting with something as the O-ring, which also under excitation can produce vibration, I again follow to my question. Therefore, is it really the right approach to control the robot in a compliant way when it's interacting with something? Is there any chance that these two elements can potentially achieve or enter resonance or some potentially not desired behaviors? Because I mean, let's just contrast it with a stiff traditional industrially controlled, kinematically controlled robot, which is always stiff, just like the ones Mathew was showing, doing the clay molding. If it's interacting with this O-ring, I don't think there will be such exchange of vibration modes. Could you possibly comment on that?
Actually, when I was a PhD student, I researched on the flexible manipulator, where its main application is the manipulator in the space. And in this case, the vibration mode is very, very important. And I worked on the vibration suppression of manipulator. And on the other hand, in case of the flexible object manipulation, I think that the phenomena which you mentioned might occur, but currently I didn't care about such vibration mode. But especially when the elasticity, rigidity is relatively high, and there may be the effect of the vibration mode. And in that case, the robot manipulator has to be controlled by considering the vibration. So by vibration, okay. I'm sorry that I cannot answer very correctly, but yeah.
Can I ask more questions? Sorry.
Yes, of course you can.
What else do we have to do tonight, right? Mathew, relate to this really nice application. I think I've seen it somewhere, YouTube or somewhere, the clay molding robot. Just based on say the part of the interest that I have on observing how something not rigid changes the shape that I call, or the configuration. In these applications, in these demos, do you need to measure the changes in this material, or is it mostly, I don't know, like an open loop, you pre-program these motions and that's it? with some model expectable result, or do you actually need to correct or some deviations or in the material behavior? I mean, is there any feedback, any sort of feedback in this?
In that clay sculpting project, no, there was no feedback, but I think there should be, and that's why I kind of advocated for it now. Is this was kind of almost 10 years ago, something like this, right? 9 years ago. So,
and the question probably is, would it help if you have some form of geometric feedback of the clay, say? Yeah,
so one of the challenges that I think the clay sculpting has and where it could go is the advantage of having done sculpture is that I kind of understood the material from myself because I used it all the time for years. So I kind of had an intrinsic understanding that when you cut it in a certain way, if the sculpture tool goes a little bit too deep into the material, then you end up ripping the clay because the clay is not water-based. It's oil and wax that's made out of the soil. So this kind of wax property has this tearing effect when the tool gets pulled out too much. And that tearing effect then deforms the surface and it rips off. So then you need to fix the surface after you've done that. An alternative is when you're used to this sculpting is how you kind of curve and rotate in order to feel that you're not tearing the material. And that's a human in the loop type of process that the person understands the material. So they change their approach to the cutting. And that is why in the video, you can see there's some gaps or some holes in the clay because the robot had no feedback. We kind of programmed it and we programmed at certain angles to approach because that was kind of how we tested a few times. This is the best angle that we could get, but it still would cause problems that a human was still able to do better, even though it was the same process. So that was kind of going to be my question to Professor Harada as well, was whether people, while they were holding these force sensors and you were doing this human in the loop process, were people saying something, or did you ask someone, okay, we record this data of how you were forcing the pipe to go on, but was the tool not the right one, or was there some response that people started mentioning that made you have inspiration for something else in how to control the robot? So sorry to like end the answer with another question to someone else.
Thanks.
I'm not sure he understood the question.
Okay, if I can rephrase for Professor Harada, my question was, you had some slides where people were holding I think there was the force sensor in order to put the O-ring, the gasket on. And I was wondering whether you used the response or feedback, not from the sensor, but from the person themselves into the design of how you were going to approach this. So it seems like you used a person to get some insight as to how you can control a robot to do this task. Was it only to record the sensor, or did you listen to anything that a person said while they were doing it that might have informed other parts of your project?
In the project, I just record the position and the force. And this is simply the purpose of our task. But currently I cannot tell what else can be obtained from the human demonstration. But this may be the future address topic. I'm sorry, I think, yeah.
Do you think typically in Mathew's clay experiment, but I think it applies in most applications, do you think it makes sense to teleoperate the robot then? If we had, at the end, it seems like that's a bit what you implicitly, I mean, at least that's what I feel from the discussion. Sometimes it seems like it would be much easier if the robot was just an extra limb and the person could manipulate clay or O-rings with the same feeling. Or maybe at least do the teaching by demonstration via teleoperation.
Yeah,
Then it doesn't solve the repeatability issue, which you say, of course. It's then you still need someone doing the same task all day, but.
Yeah, you would also, I think, lose a lot of the precision that the robot has an advantage of. And so I think it's not just teleoperation, but it's also like haptic feedback with the teleoperation. So it's not that you can just use a 6-axis device to have the robot do the motion, but because what we're discussing is about how the feedback the person receives and how they adapt to the material. So you would need that same feedback, but I'm not sure it scales either. So we show like a chair size, but what if you want to make a boat, right? Then you need such a large teleoperated system that the person could feel, and now they have to sculpt an entire boat. I think it becomes a little bit too much. So it's probably easier, quicker to get to that point, but I don't think that it's a long-term solution for what the value that robotics could play in deformation.
Maybe you said that the torque control allowed to have a RAS model of the object, and because we can't model everything, and maybe the question is, could we use also, do we need human in the loop if we don't have the model, or is it possible to do things without the human in the loop? And because you said that with the clay, it's obvious that we can see some deformation. You said that there are some holes in the clay. So maybe there is either something to do with human feedback to know when these holes have happened, or maybe the human can help to model. I don't know, or maybe we can use both torque control and vision. What do you think about this? How we can do to have a rough model and still be able to manipulate these deformable objects or materials?
So I think for one part, the vision is definitely something I had been thinking about for a while, because it was something that seemed so obvious that I could see that there's a hole, or I could see that the surface wasn't right. So if you had a scanner on the robot and it could detect there is a problem, then it would pick up a piece of clay and push it onto that problem and recut it itself. So I think in that case, there is a definite place for that approach. The comment I was making more towards we can't model everything was just thinking back to my time in Jihong Park's lab, where the guys in the lab would show this awesome humanoid robot in a simulator balancing on a little peg, and they're like, yeah, look, it works, right? And you bring it into the real world and they say, well, there's things we can't model. Like, we don't know exactly the friction of the joints and the motors, and the manufacturing tolerances are not exactly perfect. So there's a tiny bit of weight off on different parts of the robot. So everything we have the HVAC system with the wind that pushes the robot over. So that's what I was more referring to as you can't model every single system in the real world down to the perfect tolerances of manufacturing the robot to the airflow of the room that the robot's going to operate in. So that was more of my focus on why I think we can reduce the necessity of modeling airflow in order to find out what's going to happen to a deformable object by embedding the knowledge in the model or control theory itself so that it can adapt and be compliant to whatever changes during that process. So they're a little bit different for me in terms of the areas of interest. Yeah.
And okay, and human demonstration is very important. to roughly estimate the parameter needed to manipulate the flexible object. But I think that there's a possibility where we can obtain parameter without using a human demonstration, because the key technology will be the physics simulation and the deep learning. And by the combination of the physics simulation with a very, very precise physics, which can generate a very, very precise physics phenomena, and by using the deep learning technology, and there's a possibility we can obtain a parameter to control the flexible object without using the human demonstration. This is the answer.
Thank you.
Thanks everyone again for joining us today. So this pre-recorded session will be sent to IROS Workshop Organization Committee, and we have three sessions. So this is the second session actually, and we will promote all three recorded video with different channels. We will stay in touch. Thanks. That's from me.
Thank you.
Thank you.
Thanks a lot.
Thanks.
So that concludes the session.
Bye-bye.
Thanks a
Ciao,
lot.
ciao.
Bye-bye. Thank you.